Okay, so I'll give this talk in English because I know it's
מכה בנו כמעט בכל יום, גם בנושאים, כמעט בכל פן בחיינו, אם אנחנו מדברים על הפן הנפשי והפן הכלכלי והלחץ שאנחנו כל הזמן נמצאים בו. והאזרחים רואים במערכת הזאת כאין ברירה. עם זה אנחנו צריכים לחיות. במהלך החקירה שלי גיליתי עוד הרבה אבות מוניטריים אחרים, אב מפנק, אב נוקשה יותר. גיליתי שאפילו אפשר לייצר איזה אב לפי הרצונות שלנו. רק שתדעו, במהלך 7 השנים האלה קמו בעולם קרוב ל3,000 מערכות מטבע מקומיות, אלטרנטיביות של אזרחים שמעשו באותו מטבע פיאט, השקל, היורו, הדולר, whatever. הביטקוין הוא בהחלט פריצת דרך פה.
Learned a lot of stuff about her transaction, so maybe you should accept it. But you see that this problem of anonymity is a serious one, and the reason it appears is because the block ledger contains a transaction graph where you can track the flow of currency, and you don't need to be 8200 or the NSA to get this information. If you just know someone that paid you or you're paying someone, you can start learning a little bit of information, and this is a problem. So there are existing solutions for this, and they are to use a Bitcoin mix or laundry or tumbler, where the basic idea is you give your coins to a trusted pool and later on you retrieve them. But the problems with this are, first of all, every transaction must now go through this mixer tumbler, and now I have to explain to my mother-in-law why is it that I need to mix the coins when I'm just going to buy a dress with that. And the bigger problem that is now evident with the implosion of Mt. Gox is that you need to trust this central pool, and that's bad. It may be acceptable if you have a lot to hide, and that's the original thing that often, or at least sometimes why people go to such lengths to mix their coins, but it's not acceptable for the average user. And ZeroCash is a practical solution to Bitcoin's anonymity problem, where you have a protocol that just is more anonymous by default. And now let's stop and ask, is this good or bad? Do we want to have more anonymity than what Bitcoin offers? And to answer that, let's first ask the same question about Bitcoin. Is it good that Bitcoin exists? It's already pretty anonymous. So is it good to have a decentralized payment system? I think a reasonable question is also to ask about information. Is it good to have a distributed, decentralized system for communication and information, like the internet? Well, the answer, I think, to both questions should be yes. And if so, is it good for such a system to leak part of your spending information to every one of your payers and payees? I think the answer to that is no. And hence, I think ZeroCash is a good thing because it solves Bitcoin's anonymity problem. But what about regulation? And this is a big, big question. I want to answer that. It's going to be up to society to agree on the acceptable regulation for Bitcoin and similar decentralized payment systems. I don't know what the right answer is, but, and the same actually applies even to the internet, but what I want to say, whatever decisions are made, the technology that goes under the hood of ZeroCash will be able to significantly help in implementing whatever policies societies agree upon, as long as they are implementable by efficient computation. And that's the main message of this talk. So I'm going to talk a little bit about surveying anonymous electronic payment system, pre and post Bitcoin, and then I'll introduce ZeroCash. I'll talk a little bit about the technology that lies underneath this system, because that's really the main thing that I'm most passionate about. And then we'll go into detail about the ZeroCash system. Okay, so going back to David Chaum's fundamental work on eCash in 1982, it was a suggestion for anonymous, fully anonymous electronic payment system, but it needs a central bank, and this central bank needs a secret key which it uses to mint coins. After that, everything is anonymous and works very well. The problems, of course, especially if you're a Bitcoiner, are you need a central secret. If the secret key is leaked out, anyone can mint coins, and you need a central trusted party. Okay? Sander and Tashma in 99 showed how to remove the need for a secret key, but you still need a central bank. The bank mints coins using this technology that that is called, not just I'm calling it, zero-knowledge arguments, and another thing called Merkle trees. We'll see those later on again. The protocol that Sander and Tashma suggested is fully anonymous. It is secretless. You don't need a secret key. And it is efficient. Modulo the following disclaimer, it is as efficient as the non-interactive zero-knowledge arguments of knowledge that you have, this cryptographic engine underneath, and till very recently these things were not so efficient, practically speaking. And a third problem that you have also with all of these systems, and does not appear in our system, is that of coin divisibility. If you want to get change from one of these anonymous coins, you really have to go through the central bank again. You can't just make the change anonymously, okay? That's a problem that previous eCash systems had, and we solve it. Okay, post-Bitcoin systems, anonymous eCash systems. The first one, and most important, is ZeroCoin. These are the other part of this ZeroCoin meets SCIPR-lab. This is work by Mears, Garman, Green, and Rubin from a year ago. And it uses efficient zero-knowledge proofs and an RSA accumulator. I won't go into these cryptographic details. It extends Bitcoin with a decentralized laundry. And now there's no bank. There's no central bank. Only a trusted ledger, the kind that Bitcoin already has. And they actually implemented it as a Bitcoin extension. But you may know that it's not used so much. And the reasons seem to be, first of all, efficiency. So one of their spend transactions is roughly 25 kilobytes, and that's too large. And it must appear on the blockchain. Another problem is that it's as the previous solutions, it's non-fungible and non-divisible. You work with single coins. So if you want to make a payment with a coin of value 2, you're already starting to leak information. The coin values are public, and that's a problem that we solve. A work that improved and solved one of the problems, that of efficiency, was done concurrently to and independently of our work. And it is work called Pinocchio Coin, Danesis, Fournet, Cole, Weiss, and Parno, appeared in the summer. And it solves the efficiency problem because now a transaction is just 344 bytes instead of 25 kilobytes. That's a big improvement. And it's based on a very beautiful system called Pinocchio. It's a zero-knowledge system that appeared roughly 1 year ago. Now, all these sizes of spend transactions refer to the biggest, the main new cryptographic thing, which is this zero-knowledge part. This system, Pinocchio Coin, it did improve or solve the efficiency problem appearing in ZeroCoin, but it introduced two other problems. One is scalability. It's harder and harder. It gets harder and harder to create spend transactions as the number of coins in the system increases. And it's also, as ZeroCoin, non-fungible and non-divisible. So ZeroCash, which is the system I'm describing today, solves the problems of all these previous payment systems. It is with the following efficiency guarantees. 288 bytes per spend at 128 bits level security level. The time to verify this cryptographic part takes 9 milliseconds per spend. The time to create it requires 3 minutes on a single core i7 running at 2.7 gigahertz. Transaction generation scales logarithmically with the number of coins, and we support up to 2 to the 64 coins, which is practically infinite, at least looking at Bitcoin numbers. And it's fungible and divisible, so we hide the payer, the payee, the denomination or value, and of course there are some usual restrictions and disclaimers. So I'm going to show you the fine print. Okay, any questions? Good. So let me just make it a little bit larger. Here's the fine print. This cryptographic engine relies on a lot of new crypto assumptions that really could use more vetting and kicking under the tires by the cryptanalysis community, okay? That's number one. Second thing, to create a spend transaction, you need a public key that everyone can see, but this key is roughly 1 gigabyte long, okay? You need to download it only once when you download the system first, but you need this key. Another thing is that this public key must be set up by a trusted party that will use randomness and then destroy that randomness. Because if the randomness gets leaked out, a party that knows this random trapdoor can forge transactions, though it cannot break anonymity, okay? So these are the main disclaimers that I want to put. Okay. Now I want to tell you a little bit about zero knowledge. So this beautiful idea, you should read about it in Wikipedia and other places. Started off with this beautiful work by Goldwasser, Mikali, and Rakov. And I just want to give you an example in the Bitcoin world. So suppose I make the following statement. I own 30 Bitcoins with a total value of 123.5. So ownership means that I know the secret keys that can spend these coins. Now, how do I prove to you this statement? The standard proof is I point to the blockchain and show you where these coins are and then sign some message with the secret key, okay? But by doing so, I am revealing the proof itself. This proof reveals knowledge about the identity of the coins that I own. In a zero knowledge proof, it's a cryptographic proof. It's a string, 288 bytes long in our case. And it has the following properties. I cannot efficiently generate it if I do not know that knowledge. If I don't know these 30 coins, I cannot generate it. If I know them, I can generate them efficiently. It can be easily verified. Again, in our case, it's going to be 9 milliseconds. And it reveals no further information about the coins. After you see it, you have no idea which 30 coins do I own. And the beautiful thing about zero knowledge is that they exist for any statement that can be captured by a computation that is efficient and involves auxiliary information like trapdoors and passwords and secrets, okay? And it's magical, it's because of this magic that it won so many beautiful awards, including the 2012 Turing Award. Okay, now to make zero knowledge proofs efficient, practically is a big, big research topic, and that's what SCIPR-lab is interested in. So the academic pedigree of the ZeroCash engine follows from a long line of research that I won't even go over, and it's close to 2 implementations. One is called Pinocchio, and the other is Snarks for C that we published a year ago. Sorry, okay. So what is SCIPR-lab? It's an academic collaboration of researchers from MIT, Technion, and Tel Aviv University seeking to bring to practice cryptographic proof systems that provide succinct computational integrity and privacy. We started in the summer of 2009. I started this together with my co-PI, Professor Ran Tomer from Tel Aviv University, with Alessandro Chiesa from MIT, and Daniel Genkin from Technion. We have another researcher that joined about a year ago, Madar Zvirza, and we got the initial funding from the European Research Council. It's still a major source of funding for our programming team that includes Ohad Barta, Lior Greenblatt, Shaul Kfir, Michael Yabzev, Gil Timnat, Arnon Yogev, and an ad. I am looking for a superb crypto and math programmer to join the team. So we met first at the Bitcoin conference. We both presented there, and we build at SCIPR-lab general purpose, very strong systems, but they're also cumbersome. Whereas ZeroCoin was looking for something simple and lean, and we started talking, and we reached ZeroCash. So now I'm going to tell you a little bit about ZeroCash. ZeroCash works over any base currency as long as this base currency has a public ledger and a consensus mechanism, like Bitcoin and other of its offspring. And ZeroCash supports, first of all of the transactions of the base currency. It has ways for converting into a ZeroCash coin and back. And the ZeroCash transactions themselves are fully anonymous. They're fungible and divisible. You can split and merge coins, and they hide the coin value, but also the coin owner, the coin payer, and payee. Okay, and you can even include in the transaction some public information or public payments, for instance, to support transaction fees. Okay, now I'm going to give you a highlight or a view of how it works, and the following disclaimer applies to everything I say henceforth. This is a simplified protocol, a lot of missing details. The real one will appear in the paper, okay, by May 18th at the latest. So we have 2 transactions. The simpler one, about which I won't say much, is the mint. It's the way you convert a base currency coin with value V, let's say V is 5, into a ZeroCash coin with the same value or denomination. I won't say any more about it because it's pretty standard and it does not use any of the fancy new crypto stuff. The one that I'll spend more time is the poor. So the poor allows you this fungibility and divisibility thing. You can take either 1 or 2 coins, take their values, pour them as if they're a liquid into up to 2 new coins that are completely hidden, including the values, and 1 public value, okay? So you can take the content of up to 2 coins and pour them. This allows you to split coins, divide them, and so on, okay? And this is the poor transaction that I am now going to describe to you how it looks. So first of all, from the point of view of someone verifying or viewing the system, let's think about a full node, a miner, we call it a verifier. So here's what you need to know. First of all, a coin, what is it? It is a cryptographic commitment to some information. Most importantly, the value of the coin, how much is it worth? There's randomness that will be used to create a serial number that destroys this coin, so you can't double spend it. And there is a public address that you can post somewhere that anyone can pay to you. Now, the coin itself hides. What you see on the ledger is not these three values. This is private information. What you see on the ledger is just the cryptographic commitment to that information. Okay. And the way a coin is controlled is by a secret address key that is tied to the public address. So here's what you need to know. The public address is a cryptographic function applied to the secret address. Okay? So you post your public address, but what you keep with you is the secret address, and you know how to prove that you really own that public address. And this is very important. The serial number is also tied to your private address by applying a pseudorandom function to your secret address and to this serial number that you already committed to. Okay, now what a full node needs to maintain is two things. It needs to maintain a Merkle tree of all previous coins. So I'm assuming people here in the audience know what a Merkle tree is, but it is a way for compressing a lot of information, a lot of coins, into one very short string. You do this by taking the information in two coins, applying a hash to them, you get a short string, you take two of those, you apply it again and again and again, you get a root. We support a tree of up to 2 to the 64 coins, meaning we have depth up to 64 that we support. Okay, so a full node needs to maintain the Merkle tree of all previous coins. It also needs a list of all serial numbers. These are the coins that are already destroyed and cannot be used ever again. And now, the crucial thing for anonymity is that no one, unless you have secret keys and know some other information, just by looking at the Merkle tree and at the list, you cannot know which serial numbers are hidden under which coin commitments, okay? And that's very important. Now, a poor transaction is a statement that says, it looks like this. It has up to 2 serial numbers of new coins, of existing coins that are now destroyed. You don't know which ones they're supposed to be. It links them to the root of the current Merkle tree, saying, hey, these serial numbers hide in some coins in the current tree. And it has this public transaction fee, VPub, think of it that way. It has up to 2 new coin commitments, right? That's where the hidden currency is flowing. And it has, the main thing is this zero knowledge proof, which is 288 bytes long. And what the full node needs to know is, first of all, it needs to verify this proof, which takes roughly 9 milliseconds. Then it needs to check that the serial numbers haven't appeared yet before. And if both of these things pass, then all you need to do is just add the coins to the Merkle tree, add this transaction to the ledger, and then just collect the transaction fee like you do if you're a miner. Okay, the main thing, okay, I don't have time to show you how this transaction is constructed. Let me just say that the main thing that needs to be done is to construct the proof. And what the proof says, I'll just show you the statement. The proof is a proof of the following statement. The person making the payment says, I know the location of 2 coins. I'm not telling you where they are, but I know that they exist in this tree that has root R. I know their values, not telling you what they are. I computed correctly the serial numbers that I'm publicly displaying. I know the hidden values for the new coins, and I even summed up the sum of the old values and saw or know or verified that the sum of the old coins equals the sum of the 2 new coins and the public value. Okay, and all of this thing is one big statement that is proved in zero knowledge. So you do not get anything more out of the proof than what you see from the statement. So you see, the statement really does not tell you anything about the location of the coins, right? Or how they're connected to the serial number. It just says, I know this thing, okay? That's how anonymity is obtained. Now, as I said, what about Bitcoin regulation? Well, because zero knowledge proofs are so powerful, if regulation would demand that you need to pay taxes or show other things, then you can add that to the statement that you're proving, and it will be supported, okay? So the techniques are very, very powerful. And I have to end up, so I just want to say, it's the first fungible, divisible, anonymous payment system based on a decentralized ledger with an implementation. And it solves Bitcoin's anonymity problem using cutting-edge construction of zero-knowledge proofs, and there will be more to come. Now, when will it be ready? You'll probably want to ask this. So here's what I can say. The paper will be published by May 18th in the Oakland Security Conference, hopefully earlier online. The code will be open sourced when it's ready. And I can say no further comments on deployment. So, and let me just repeat again, if you like this stuff and you know your crypto and math and you know the program very well, please talk to me. We're looking desperately for good crypto math programmers. Thank you very much.